Hello everyone, we are researchers from National Yang-Ming Chiao-Tung University in Taiwan. Let me introduce our work about removing visible seams and very large stain normalization results. Histopathology is a key field in medicine. It involves the examination of human tissues under a microscope to understand the manifestations of diseases. A key requirement is that all tissue samples need to be chemically stained so that they can be visually inspected by pathologists. However, a key problem of the staining process is that the stained images can have large variations in terms of colors, shapes, and textures. This makes human inspection and downstream computational tasks difficult. Therefore, many computational methods have been proposed to virtually transform one kind of stain images to another. Such methods serve two main purposes. First, to transform multiple stain images into a common color space. Second, to transform stain images into novel stain styles that are more difficult to obtain physically. Like many medical image applications, most state-of-the-art methods are now neural network-based. However, for very large image inputs, which are common in practice, it becomes necessary to first partition the image into multiple smaller patches and run the neural network separately. This led to the key problem that the synthesized contents may look different between patches, causing color differences between patches and visible seams at patch boundaries. These artifacts are bad to look at and hinder performance of downstream computational tasks. Existing stain normalization methods proposed various solutions to minimize the color differences between patches, but the visible seam problems still remain. Some examples of such visible seams are shown on the right. We tried traditional image blending methods to remove the seams, but they were not able to satisfactorily remove them. Therefore, we propose a novel two-step pipeline to remove the seams specifically. In the first step, we leverage a neural network to synthesize novel contents to replace the regions at the patch boundaries. We use the Pix2Pix neural network and found it works quite well. In the second step, we further refine the results by an alpha blending process. We explain neural image-to-image translation methods as follows. In short, if enough samples of images of source and target styles are given, such neural networks can quickly and reliably transform images of the source style to the target style. For example, transforming a black and white sketch image to a fully colored image. Some methods require paired image examples to work, while some other methods don't require the image examples to be paired. In our method, we use Pix2Pix, a robust and powerful method for paired images, to transform stain images with seams to corresponding images without seams. To generate the training data for the seam removal neural network, which are pairs of stain images but one has no seams and one has seams, we invent a novel data generation approach as follows. We first conduct a standard pass of stain normalizations using the default patch subdivision. We conduct a second pass but with a different way of patch subdivision that interleaves with the first one. In this way, we now have overlapping stain normalization images, one has the seams and one has no seams. We then use these paired overlapping images to train a Pix2Pix neural network to convert the images with seams to the corresponding images without seams. Because there may be slight visual discontinuities between the parts that are processed by Pix2Pix and the other unprocessed parts, we propose a post-processing step to remove such discontinuities. In short, we conduct an alpha blending process with a novel spatial varying weight, so that two kinds of images are smoothly blended. We now explain our experiment results. We tested on the public ANHIR dataset of very large real-world medical stain images of several stain styles. In particular, we tested the conversions between the standard H and E stains and the Ki67 IHC stains. We also tested on a real photo dataset of scenery images shot in summer and autumn times in Kyoto. This dataset enabled us to test conversions between photos of summer and autumn styles. We compared with four key methods for removing color inconsistency between patches, namely the traditional Poisson blend-based approaches, the standard instance normalization layers in Cyclic-GON, the kernelized IN layers proposed in a ECCV 2022 paper, and the thumbnail-based IN layers proposed in a I 2022 paper. In summary, we found that Poisson blending methods could not effectively remove the seams at all. Meanwhile, our seam removal method significantly improved results by the current SOTA neural methods quantitatively and qualitatively. We show experiment results as follows. Measured by commonly used FID and CORR scores, our method improved existing IN and KIN-based results by large margins. For TIN-based results, due to their inferior initial quality, our method did not improve them much. Our method also improved upon IN-based results on the Kyoto dataset significantly. For qualitative results, through close visual inspections, we see that the visible seams are consistently and satisfactorily removed by our method in the medical image dataset. Tested on the Kyoto Real Photos dataset, we also see satisfactory seam removal performance by our method. We now show our experiments about downstream computational tasks. We note that stain images are also often used as image inputs for tumor classification. Following a previous paper, we use SqueezeNet as the neural network method to classify stain images into normal or abnormal cases. We then conducted experiments to verify two things. First, we want to check if the visible patch seams really have negative effects on tumor classification performance. Second, we want to verify if our method really improved tumor classification performance on the patch boundary parts. Our quantitative testing results verified that, yes, tumor classification method did perform worse on the seams. And our seam removal method did improve classification results on the patch boundary regions by a small margin. In conclusion, in our research, we identified that even today's soda stain normalization methods still have pretty visible seams at the patch boundaries. These seams are not only bad to look at, but also hinder the performance of downstream tumor classification tasks. We then proposed a novel approach that leverages both neural networks and optimizations that can consistently and effectively remove the seams. Thank you for your listening, and we are happy to answer questions.